All right, so we're on section 1.4, shifting, reflecting, and stretching graphs. I didn't think there was stretching in here, but there is. But that's okay. But one of the goals of this course is to enable you to build an intuition for what these graphs are going to look like so that when you type it into a graphing calculator and you look at the picture, you'll kind of know that, okay, yeah, that's looking how I thought it was going to look. So it starts off with, we did a quick review, a sloppy review maybe, of parent functions. So this section starts off with those two. So I have those recreated on this first screen, the main ones that we do. So let's look at each one of them. So here is parent function, linear function, y equals x. So pretty self-explanatory there. And we just are going to be doing things like shifting, reflecting, and stretching these, though that's not very exciting with a line. The next one that we talked about was the absolute value function. So when we're looking at absolute value function, remember absolute value just means make whatever's inside here positive. So it's positive. Instead of continuing down here like the line, it goes back up here because it's making everything positive. All right, over here, quick review again, is a square root function. So the square root of x ends up looking like this. So this is the parent function for the square root. Down here, we have the x squared, or the quadratic function. So this is the parent function. Notice it's an even function. It's symmetric on the y-axis here. And our cubic function. So notice this is symmetric about the origin. So talked about that yesterday as well, but there's a review for you there. And our rational function, this is a new one. I didn't talk about this in the last lesson, but rational functions we'll end up looking at as well. And they look like this. They're symmetric about the origin. So they're kind of interesting functions to deal with. So let's move on from there. And there's a good screenshot for you right there if you'd like. But go ahead and let me know down in the comments what questions we have on this. Are we doing a good job explaining this? Are there any that you think we're missing? Oh, things like that. In this section, we'll be talking a lot about transformations. So transformations, think a geometry class you used to call like a translation, which is a transformation, a slide. A reflection was referred to probably as a flip. You talked about dilations, which reduced and enlarged images. But in Algebra 2 pre-calculus, we referred to them as stretches. And we're only going to be talking about vertical stretches today. Horizontal stretches are a thing, but that's coming up in a future lesson. So let's go on to some examples. So first things first, we're talking about translations. So that means we're sliding a picture around the graph. So in pre-calculus, we call these shifts. We have vertical shifts and horizontal shifts. So here's the way it looks algebraically down here. If I have a function and I add something, call it c, that's going to shift up c units. If I subtract c, that shifts me down c units. If I'm inside the parentheses of the function, this is counterintuitive, but the plus c actually moves it to the left. That's why I put an underline in there. But it moves it to the left c units. And when we have a minus inside the parentheses or inside the function, we're shifting to the right c units. But with all of these, we're not changing the shape of the function. We're just moving it up, down, left, and right. And in case you're wondering, yes, they can be combined so that you can shift, say, to the right and then up a certain number of units. So we'll look at examples of all of these. So let's get on to the next slide. Let's look at an example of doing some of these transformations or translations. We're talking horizontal and vertical translations. So all of these, by the way, which we'll get into on the last slide, are called rigid transformations. That means we do not change the shape of the graph at all. We're just moving up, down, left, or right. So let's look at the first example, which is from page 43. So I could call that, let me go to 43. I changed it up a little bit just to make it a little bit simpler. That's a bad 3. But instead of x cubed, I made it x squared because we're familiar with what x squared looks like. The first thing, just like in Algebra 1 and Algebra 2, is you start with the parent function. So that's graphed in red right here. So f of x equals x squared. Then we're doing something to that x squared. And that something we're doing is we're subtracting 1. So we're moving it down a 1 unit. So the blue graph is the exact same shape as the red graph. It's just translated down 1 unit. Let's go over to part B of this example. So again, we're looking at f of x equals x squared. That's the parent function. Again, it's graphed in red. But now we're doing, it's similar to what we looked at before. Here we had just x squared minus 1. Here, the minus 1 is inside the parentheses. So remember, this is that counterintuitive one. You would think it moves it to the left, but it does not. It moves it to the right 1 unit. So I look at my parent function, which is in red, and its origin, the origin is its vertex, and that vertex gets moved over 1 unit to the right because of the minus 1. But notice the shape, the blue curve, is the same shape. It's just been translated 1 unit to the right because of this minus 1 in here. And then last but not least, we had, we're going to put a number inside the parentheses, so x minus 1. Then we're going to add 1. So this is what I was saying when we can, do 2 things to a function, or we could do 3 things or 4 things. But for now, here's the parent function. That's the red curve, x squared. And we are moving it to the right 1 unit. So that's what this arrow here is for. Taking the vertex and moving it to the right 1 unit. And then I'm moving it up 1 unit. So the vertex goes from here up to here. So the blue curve is the same shape as the red curve. So because it was just a transformation, it wasn't, or a translation, it was just, think of this, used to call these slides in geometry class. We have not changed the shape of this curve because, like I said, in a future slide, we'll talk about the rigid, this is what's called a rigid transformation, right? It does not change the shape of the curve. Okay, let's go to the next example. Example 2, also on page 43. So this is somewhat similar to the previous. We're just doing 2 things to this graph. So in blue is my parent function, right? It's just x squared. And then I am moving this, plus 1 means counterintuitively moving 1 unit to the left. So I'm moving this 1 unit to the left. That's an arrow. And then I'm moving it 1 unit down because I have a plus 1, which moves it 1 unit to the left, which is what I did first over here. And then minus 1. This minus 1 moves it down 1 unit. So again, forgive my drawings, but the red curve is identical to the blue curve. So the blue curve is where we started with our parent function, and the red curve is what happened after we translated it, or translated it. So it just slid to the right 1 and down 1. Example 4, page 45. So parent function is given as f of x equals the square root of x. So that is graphed here. Remember, we always start with the parent function. And then we're going to take the opposite of that function. Well, the opposite of this function just means you're moving it down underneath the x-axis. It has the exact same shape. It's just been reflected across the x-axis. Like this x-axis is kind of like a mirror, right? I'll write that in there. This is a mirror. If I can write neatly. There we go. So again, a reflection. So this is a new piece of information here. But again, it's a rigid transformation, right? Remember our word rigid? We're going to get into this in a future slide. But it's a rigid transformation, meaning it does not change the shape of the function, the parent function. All right, let's move on to part B, which is down here. So part B, I guess I could bigify that. So part B ends up looking, we have the parent function right here, f of x is the square root of x. Then we're taking its opposite. So if I take the opposite of a function on the outside, like up here, and it flips it across the x-axis, what do you think happens when we take the opposite of the x on the inside? And if your guess was we flip it on the y-axis, then you're exactly right. So flipping inside, remember this is like being inside the parentheses, but I'm inside the square root symbol. Instead of flipping it down here, it's flipping it over here. And then the last example we have, we're doing two things to it. Make that a little bigger. So again, parent function in red right here. So I'm shifting it 2 units to the left. So 1, 2. But then we are flipping it. That's this minus sign I circled out here. So it got moved to the left, but then it got flipped over. So we did 2 transformations there. We moved it to the left 2 units, and then we just reflected it across the x-axis. Okay, so again, go back and re-watch these if you need to as many times as you want. You can stop, rewind on YouTube. And if you have any questions, put them in the comments down below on YouTube, and I will be happy to address those. Now from page 46. So remember I was talking about the rigid versus non-rigid transformations. So rigid is just what the word rigid means. It means we are not changing the shape of anything. Those include like horizontal shifts, vertical shifts, so horizontal left and right shifts, vertical shifts up and down, or reflections, and they can be reflections across the x-axis or the y-axis, but the shape of the curve does not change. So those are called rigid transformations. As opposed to, go down here, we have a non-rigid. So there's rigid, which doesn't change it, and non-rigid. So this is what we're going to be getting into here. We're going to be doing some vertical stretching and shrinking, and not in this lesson, but eventually we'll be looking at horizontal stretch and shrink. But for today, it's just vertical stretch and shrink. Now let's check out example 5 on page 46. So we're dealing with the parent function, and it's the absolute value function, f of x equals the absolute value of x. So we graph that in red down here. So it graphs this way. So when x is 1, y is 1. When x is 2, y is 2. So on. When I go left, when x is -1, the absolute value of -1 is +1. The absolute value of -2 is +2. So that's why this is shaped like this V. But now let's suppose we want to stretch it, okay? So we're going to call it h of x, and then we're going to multiply the absolute value function by 2. So that means that when x is 1, the absolute value of 1 is 1, but then we multiply it by 2, so that puts us up here. The absolute value of 2 is 2, but multiply that by 2, and it puts us up here at 4. Then when I go left, the absolute value of -1 is 1, but then double that, puts us right here. The absolute value of -2 is 2, but double it, and it puts us up here on this blue line. So if you notice, this blue function is a vertical stretch. It's like you grabbed the top and bottom and pulled it up and down so that you're stretching it out, right? Kind of like how when you used to smush a, I don't know, silly putty onto a comic strip, and then you would see it and you could stretch it. It was kind of a cool thing you did when I was a kid. We didn't have cell phones, so give me a break. But that is a horizontal stretch. So this number here, it's not in the text yet, but we're going to be calling that A times a function. Whenever this A is greater than 1, it's going to result in a vertical stretch like you saw right here. When this A is less than 1, right, less than 1, forgot my 1 there, less than 1, it's going to be a vertical shrink. So it's like you're smushing it down, the shrink. The shrink smushes it down this way from the bottom and the top. Let's look at an example, same screen here, but same function. We're looking at f of x equals the absolute value of x, only this time instead of multiplying by 2, we're multiplying by a half. So this is that A I was just talking about. It's less than 1, so that's going to result in a shrink, a vertical shrink. I should write vertical shrink. We're going to do horizontal shrinks at a future date. But for here, notice, let's go to 2. The absolute value of 2 is 2, which puts us up here on the red curve. That's my parent function. But I take half of that, and I'm down here at a half, or at 1, I guess. Same thing, I go here. Left one is absolute value of negative 1 is 1, but half of that puts you back down on the blue line. So if you notice, this blue function looks like it's kind of been smushed down from the top and the bottom, right? It's been smushed in this way and smushed up this way. Smush is not a math word, but people understand what smush means. But that is a vertical shrink of this function. And that, my friends, is the end of section 1.4. So as always, leave a comment down below. I'll respond to those. Or you can just text me on my Google Voice number if you have questions there. But anyways, thanks for watching, and I'll see you in class.